And are having a special lecture series in honor of the 150th birthday, I guess, of the periodic table. Its discovery or formulation, invention, whatever you want to call it, by Mendeleev. And we decided to have a series of talks by people in different disciplines. So, the first talk was by Jim Saul, who I saw just walk in the door. And he gave a talk about the Big Bang and how the Big Bang created various elements. So that was an astronomy-based talk, but we also have some talks related to various other sciences and how the periodic table has influenced everything. Today I'm excited because I'm a mathematician and we have our math talk of this series. And it was actually John was the natural choice for this talk because there really are not that many mathematicians around that actually understand all the kind of stuff he'll be telling us about and are able to explain it in a way that's understandable for everybody. And John is a very gifted expositor. So just to tell you a little bit about John Baez, he got his PhD from MIT and now is at UC Riverside and has also worked regularly as a kind of part-time position in Singapore at an Institute for Quantum Technologies. But John is very well known in the math and physics communities for his expository writing. He started a blog before there was such a thing as blogs and the World Wide Web back in 1993. He started writing a weekly column called This Week's Finds in Mathematical Physics, which really was a prototype of the way people communicate nowadays about these kind of ideas. And so some people have called that the world's first blog. John has also won awards from the American Math Society, the Levi Conant Prize, and other awards. He is also the first cousin of John Baez, the famous singer that many of you will know, and who was my dad's very favorite singer of all time. So there's many reasons that we're excited to have John, but most of all because he's really a gifted expositor and an expert in mathematical physics who I think is going to tell all of us things that we didn't know before about the mathematical mysteries of the periodic table. So it's my pleasure to introduce John Baez.
Great. Thanks. I didn't bring my guitar. You'll be relieved to know. So it's a great honor to speak at this anniversary of the periodic table. I've always been fascinated by chemistry, and in particular the periodic table, because chemistry is a subject that's sort of halfway. Should I do something? No. Chemistry is a subject that's halfway between physics and biology. So physics, ideally you write down some equations describing some laws and you can completely solve them, ideally on a pad and pencil, with a pad and pencil. And simplicity is its goal. Biology shows that the ramifications of the simple laws of nature can be endlessly complicated and unpredictable and fascinating. And chemistry is somewhere in between, where you almost think you can understand it mathematically, and yet it still shows an incredible diversity of consequences. And the periodic table of elements illustrates that. You have, ultimately, they're all different solutions of some equations, these different elements, but they all have their own personality. So chlorine smells funny like chlorine, and then there's some metal that's liquid at room temperature, and there's some metals that are radioactive, and this and that. And so you can begin to see how the simple laws of nature can produce this wonderful world we're in. So I won't get into too much of the complexity. I'll start out with the periodic table, and I'll really focus a lot on the very simplest thing, but the simplest element, the first one in the periodic table, is hydrogen. So it just has one little electron orbiting one little proton. The proton is not huge and green like it is in this picture. That's just what these people did to make it be able to fit the letter H in there. But it turns out that understanding this simple element, as I'll try to explain, sort of illustrates, sort of leads you to understand the periodic table to a large extent, although certainly not completely. So then comes helium. So helium is an extremely inert gas, sort of the opposite of hydrogen in the sense that the Hindenburg Zeppelin caught on fire because it was full of hydrogen. If it had been full of helium, we wouldn't have had that problem. And the reason why it's so inert is because its two electrons orbiting the nucleus fill a shell. So the electrons can have different amounts of energy, and the shells are basically those different kinds of energies that they can have. And so when you have two when you fill a shell, no electron wants to move up to a higher shell because that would take energy. And so they're very content there, and they don't really want to react or do anything when they meet other atoms. So it's called an inert gas, or sometimes you call it a noble gas. The idea being that noble folk don't bother to associate with the rest of us. And so then comes lithium, and that's sort of the opposite. It's an extremely reactive metal because it has one electron too many. So you've heard, I'm sure, like two's company, three's a crowd. Well, that's what's going on here. There's this third poor electron hanging on there that doesn't really want to be there too much because it has a lot more energy than its partners, and so it's eager to react with other atoms that will accept that electron. Then comes beryllium. That's also metallic. The presence of extra electrons in the outer shells is what makes metals be metal. The reason why metals are shiny is because there are a lot of electrons roaming around that can easily hop from one atom to another, and so when light comes along, it interacts with those electrons very strongly, and the light just bounces back. So that's a less reactive metal. And then comes boron, which is the most boring element in the periodic table, so I won't say anything about it. And then comes carbon, which has 4 electrons in this second shell. It will turn out that the second shell can hold 8 electrons. So this guy is exactly halfway full. And so that means that it has this desire either to get rid of those 4 electrons or to take 4 more on. Sort of equally, it's balanced between the two tendencies. And so it's a very exciting atom. It can form all sorts of molecules. In particular, one of the simplest ones, you could just give it 4 hydrogens that would contribute 4 more electrons to fill that second shell, and you get methane, which is CH4. But it can do tons of stuff. We're all made of it. Nitrogen has 1 more electron, so it's just 3 short of filling the second shell. So it would be very happy to take on 3 hydrogens, and if you did that, you'd get ammonia, which is again a very fundamental chemical. There's lots of ammonia in the atmosphere of Jupiter, for example. It's very easy to make that stuff. And then comes oxygen, which has just 2 electrons short of filling the second shell. So it would love to connect to 2 hydrogens, and it makes water, this wonderful substance that's all over the place and very fundamental in biology and also all over the universe. Then fluorine is just 1 short of filling the second shell. So it's really just desperate to get 1 extra electron. So fluorine is an extremely reactive and basically nasty chemical. Like you can etch away at glass with fluorine, and if you talk to chemists, they'll say like working with fluorine compounds is something you got to be careful with because you can get in all sorts of trouble. It's so reactive. And then neon has filled up the second shell with all 8 electrons. So like helium, it's very inert. And so the pattern continues. I'm not going to spend the whole talk going on up the periodic table. But as you know, it looks like this. And I've basically gone through the top 2 rows there, and you'll notice that there are interesting, mysterious mathematical patterns. The first shell, or the first bunch of the first row of the periodic table has 2. Then the second one, which we went through, has 8. Then you see that the next one also has 8. But then you get these longer ones, and they have 18. These longer rows have 18. But then actually, if you examine them, you see that these later ones really have more than 18. But because they didn't want to make a periodic table that was like so long it couldn't fit on the blackboard, they put a little asterisk here and they say, oh yeah, by the way, there are all these guys in there, these rare earths. And similarly here, there are all these guys, these actinides, which are so heavy that they're radioactive. Their nucleus is not so stable. But the numbers 2, 8, and 18 are what I want you to take away from this periodic table. And I want to try to give you some explanation of why those numbers 2, 8, and 18 show up. So the reason why the periodic table is pretty complicated in some ways is that the electrons are all interacting with each other. Electrons are all negatively charged. They repel each other. And so to figure out what they will do to minimize their energy is pretty complicated. They're all trying to stay away from each other. But if you didn't have that annoying tendency, if the electrons didn't notice each other, then the periodic table would be tons simpler, and you would just see that the first row of the periodic table would have 2 elements, which it does, hydrogen and helium, and it would fill up the first shell, and then the next row of the periodic table would have 8 elements, which it actually does, and that would be filling up the second shell, and then you'd see that the next row has 18, and you see that there it breaks down. That's not exactly what happened. We had 2 rows of 8 before we got to the 18, and so on. And it would turn out that in this simplified world where the electrons don't interact with each other, you would get this very beautiful, simple pattern of these shells where the number of electrons in these shells would be just twice the square numbers. 2 times 1 squared is 2, 2 times 2 squared is 8, 2 times 3 squared is 18. And I want to try to say a little bit about why that's the case, because there's a very beautiful and quite elaborate mathematical reason why, but I just want to give you a sort of an easy intro to that. So what are these pictures here? These pictures are nothing very profound, but maybe they're a little bit profound. So they're mainly just mnemonics to help you think about twice the square numbers. So the number of boxes in this picture will be a square number because the picture is a square. But because we want to get twice a square number, I've chopped each little box into 2. But you see there's also something else going on here, which is little squares fit inside bigger squares in a nice way. And that turns out to not just be a math thing. That's something that's actually going on in the chemistry, that the different shells will have these, sometimes they're called subshells in them. So this shell with 18 will have first 2 that play some special role, we'll see, and then we'll have, I guess, 6 more, and then we'll have whatever this is more, but they're all multiplied by 2. So it's better just to think of it like 1 box plus 3 boxes plus 5 boxes, adding up for a total of 9 boxes, which gives you 18 when you double it. And this pattern turns out to actually have it's a real thing, and it really shows up in the chemistry and the physics, and I want to try to explain that to you. That's my goal. That's all I'm trying to do. My announcement of my talk made it sound like I was going to talk about mysterious things that people still don't understand about the periodic table, but I realized that even explaining the things that people do understand will take so long that I just want to talk about something that pretty simple and yet still, I think, pretty interesting. Okay, so the first question is, what is a shell anyway? So although I drew them in this cute way as like rings of electrons, first 2 in a little ring and then 8 in a bigger ring, that's not actually what's going on in an atom. That's an old theory of atoms. Niels Bohr, when he was first trying to understand what we now call quantum mechanics, which is the theory that describes what electrons do, He had a theory that the atom was made of electrons orbiting the nucleus in circles, and he tried to come up with a theory for what the different energies of these different shells were, and it was partially successful, but we now know that it's oversimplified, and Bohr later learned that it was oversimplified. It was a great triumph because it led people to realize the deeper theory that we now call quantum mechanics. But I want to get beyond this simple picture here, because that's not really what atoms look like, and I think we should all learn, if you don't already know, what atoms look like, and a little bit about why. So now I have to give you a micro course on quantum mechanics, which is a great subject. It's an amazing subject, and usually people manage to completely muddy it and make it sound like, oh, some scary, mysterious thing. It's definitely mysterious in some ways, but it's really simple in some other kinds of ways. So people first got the idea of it from trying to understand light. There was this big argument starting before Newton about whether light was a wave or a particle. They knew that light seemed to go somewhere. And two things that go somewhere are particles. You can throw rocks at someone, and waves. You can have ocean waves going from some place to another. So those are two obvious guesses as to what light could be. And the answer is that it's both. That was the final solution to that argument that went on for centuries. But if you think about light as waves, what's nice is that the different colors of light correspond to waves of different wavelengths. So red is more stretched out, longer waves than violet. And that actually leads us to notice some interesting things. So in the vacuum, so not in that prism, the prism is breaking up the colors of light because light goes at different speeds in glass. Different colors of light go at different speeds in glass. But in the vacuum, in empty space, or almost practically in air, that'll be pretty close to a vacuum, the light of all the different colors is moving at the same speed. So that just means that the light that has the shorter wavelengths will be wiggling up and down faster. So you can see that these are both moving at the same speed here, but because it has more wiggles, the number of wiggles per second that you see is higher with the blue light. And that's called the frequency, the number of wiggles per second. Now Einstein made this great discovery. You may have heard of Einstein and E equals mc squared and all that jazz, but he did not win the Nobel Prize for that. He didn't win the Nobel Prize for special relativity or general relativity, because those discoveries were so far out that Einstein was dead by the time people really agreed that he was right. Or more precisely, that enough people on the Nobel Prize committee went along with him. There were some people there who were pretty slow to catch on. But what he won the Nobel Prize for was this discovery that light not only can be thought of as waves, it's also made of particles. Now that sounds like a contradiction, which is why people think quantum mechanics is weird, but he discovered that in some experiments you can really tell that light plop, plop, plop hits a photographic plate as individual particles, and they got called photons, for particles of light. And Einstein figured out what the energy of a photon is, and it's just the rate at which the wave wiggles per second, called its frequency, which is written with this Greek letter nu that looks just like a V in this font here, times some number, which is a very fundamental number in quantum mechanics, but doesn't needn't concern us much here. It's called Planck's constant. So the energy of a photon is just how rapidly it's wiggling times some number. So energy, basically, they realized, the essence of energy is how fast things wiggle, which is nice and simple. People should know that. And later on, people realized that that's a general rule, that every kind of matter is made both of waves and of particles. There's no real fundamental difference between waves and particles. So how in the world could that be? Well, there's a long story behind that, but you could briefly say that the wave tells you how likely you are to find the particle at some particular place at some particular time if you look for it. So if, for example, if you trap a particle in a tiny little box, and I'm imagining a one-dimensional box so that the particle can just like go back and forth between here. We're not worrying about the other directions. This is one kind of thing it could do. This blue thing is basically describing the probability that you find the particle somewhere or other in that box if you check to see where it is. And you can see that that's waving. So there's a wave that's describing the probability of finding a particle. And that's the rough idea of how matter gets to be both waves and particles. It turns out that the waves are the things that satisfy the nice laws of nature that you can write down equations for. But what the waves are is they tell you how likely it is that you find a particle there. And then in this marvelous picture of quantum mechanics, it turns out that the stuff we saw about light is true for everything. The energy of anything is just the rate at which its wave wiggles, its frequency, times Planck's constant. So I get lots of email from crackpots who like to convince me of their theories by writing them in all capital letters with lots of exclamation marks, because they've decided that that's like the most authoritative way to state a crazy new theory. So this sounds like one of those crazy new theories, but this one actually happens to be true, unlike most of them. Matter is waves, and energy is the rate at which these waves vibrate. So that's astounding. You should not believe it if someone just walks up to you on the street and tells you something like that. And even though I'm standing in front of a podium and they say I'm from MIT, you should still be a little suspicious that this crazy theory is true. And I'm not really going to have time to try to convince you that it's true, but I should say that like the reason why I, for example, believe in quantum mechanics is that there are specific equations describing how these matter waves vibrate. It's not just like, matter is waves, everything's waves. It's like we know the formulas that say exactly what these waves do. Furthermore, we can use these formulas to predict what happens in hundreds, and I really should have said thousands, of experiments. Like we can calculate the properties of chemicals using these formulas. We can calculate the properties of different kinds of light or subatomic particles. And then thirdly, and most importantly, the predictions that you get from these calculations, they're right. They always work out. So that's the kind of standard of evidence you should demand for some wacky sounding theory, like saying that matter is all waves and energy is the rate at which the waves vibrate. You don't just say like, oh, that sounds cool. No, you have to really test it and get much more specific. But of course, that takes a lot of time. And this talk is not supposed to be a course on quantum mechanics. So I'm not going to go into that too much. But I should say, although it takes a lot of time to learn this stuff, there's nothing more fun than this. There's really no better way to spend your time that I can think of. But I would say that, right? Because I'm a mathematical physicist. Some people like watching football. I like this kind of stuff. So to get you the idea of how you could have an equation that describes waves, let's talk about an equation that describes the vibrations of a drum head. So if you have a circular drum, if you hit it, the drum head is wiggling up and down. You can't really see it wiggling up and down unless you look super closely, but it is, and that's what makes it shake the air and make sound. And there's this equation, which is just called the wave equation, which describes how that happens. So here, psi, this Greek letter, tells you the height of the drum head. And of course, the height depends on where you are on this disk, this drum head, and it also depends on the time. So psi depends on the position and also on time. T here stands for time. C, you may have heard of C as being the speed of light, but here I'm just using it to mean the speed at which waves move around on this drum head. If you had like a huge drum, you could like hit it in the middle, boom, and this wave would shoot out in all directions, and you could measure the speed at which it moved, and that would be the C here. And what this equation says is this. This funny thing is saying how much the height of the drum head is accelerating. It's either could be accelerating up, that is moving up faster and faster, in which case this would be positive, or it could be accelerating down, in which case this would be negative. And indeed, if you watch the drum head, you see that that's happening. If you look at any little piece of the drum head, first it's accelerating up, then it's accelerating down, then it's accelerating up again. And this says that that acceleration is equal to this number times this goofy thing. What this thing is this thing, well, it's called the Laplacian, but that doesn't tell you anything. What it is it's telling you how curved, and I've got, I've got it right, okay. So I thought I got the sign wrong. So it tells you how much the drum head is curved. So you could have a drum head that like at one point was like curving down in all directions near that point. And then this thing here would be negative. And then this equation would say, well, if that's the case, then then this is going to be negative too. And so then the drum head is going to be accelerating down. So if you have a little piece of the drum head that's curved like this, it's going to accelerate down. Whereas if it's curved the other direction, it will accelerate up. And then there's other subtler combinations of things that can happen. But this basically says that the drum head is, if it's like poking up, it'll be probably curving down there. And so then this will accelerate down. When it's down, it'll be curving up around there, so it'll accelerate back up. So people can solve this equation, and then they can figure out what the drum head will do. And this is the kind of thing you do in physics grad school or undergrad school. And there are lots of solutions to that equation. So here are a bunch of these, here are 9 of these solutions. These are not by any means all of the solutions, these are just a few of the solutions. These are some very particularly nice solutions called standing waves, where what's happening, as you can see, is that first of all, they just keep repeating themselves over and over again, which is good because an animation would run out of the room if it kept doing something different all the time. So it's a loop. Each of these little animations is a loop. And you can see, furthermore, that the overall shape of the wave is basically the same as time passes. Like this simplest one here, this one called 0, 1, it's basically just shaped like this. But it could be negative that, so it could be shaped like this. And all it does is it just keeps switching back and forth between those two. This is a little fancier, but you see it's like a sombrero or an upside down sombrero, and it just keeps switching between the two. These are basically, well, I'm lying slightly, but basically these kind of things are all you get when you get standing wave solutions. But they're actually lots of them. So notice these ones here are circularly symmetric. This first row, this first column of them, these are the ones that if you rotate them a little bit, they look exactly the same. Like it's the same height at all points along any one of these circles in the drum head. So the only choice you get once you say that it's circularly symmetric is the number of wiggles as you go from the inside to the outside. So that's what this 0, 1, 0, 2, and 0, 3 means. This basically has one wiggle. This one has 2 wiggles, like it wiggles up and then it's also wiggling down. This one has 3 wiggles, and you could go on. There'd be infinitely many, 4 wiggles, 5, and so on. These are fancier because these are not circularly symmetric. If you go around one of these circles, it's not always the same height. But if you look carefully, you'll see that as you go around one of these circles, it's probably best to look at that top one there. You'll see that like if you followed your finger along it at one instant in time, it would go up and then down. So it has one wiggle as you go around, and that's what this one in front means. So these all have one wiggle as you go around, and any number of wiggles as you go from the inside out. So they could have 1, 2, 3, etc. These guys have 2 wiggles as you go around. And again, it's easiest to see on that top one. You can see this has like 2 places where it's bulging up and 2 places where it's bulging down. To me, that counts as 2 wiggles, not 4, okay? Because it's like a wiggle means like going up and then back down. So this one's called 2, 1 because it has 2 wiggles as you go around and 1 wiggle as you go out. This is 2, 2, this is 2, 3, and it goes on forever. So there'd be like one called 5, 7 or something like that. And people know the exact formula for all these standing waves, and they can figure out the frequency of all these standing waves. They can figure out how fast they're vibrating. And that's important for us later on, because later on, when we get to quantum mechanics, those frequencies will be energies. They're not the energies for these drumheads, but they are when you get to quantum mechanics. So that's a sort of a simple example of how you can take a wave equation and solve it, find the standing waves, and then and classify the standing waves by some list of numbers, and use that then to understand the whole problem. So it turns out using these basic guys, you can then go ahead and figure out anything that the drumhead could do. Anything the drumhead could do would be some kind of mixture of these basic possibilities. So, okay, here's the high point of the talk, or the low point, depending on what your attitude is towards equations. So this is like the last equation. But it's also the most important equation by far, because this is the equation that says what an electron does when it's in a hydrogen atom. So there's more fancy equations that describe when you have like lots of electrons and lots of atoms, but I wanted to keep it simple and just think about one electron going around one proton. And it's already complicated enough that you would like easily spend a few weeks in a physics course studying this equation and how to solve it. It's called Schrodinger's equation. It's a special case of Schrodinger's equation. Schrodinger was the guy who figured out the kind of wave equation that describes matter waves. And they looks like this, or souped up versions of this. So it's more fancy than the other equation I showed you in a number of ways. So first of all, we've got this wave function that I'm again calling psi, the Greek letter psi. And it's this wave that depends on time and place that describes what the electron is doing, like how likely it is to find it in different places. There are some subtleties that I'm going to tell you about in a minute, but that's the basic idea. In this equation, Planck's constant shows up. Planck's constant shows up all over quantum mechanics, but in this case, it shows up divided by 2 pi, and that happens so often that Feynman made up a name for it with an H with a little cross bar on it. Physicists call it H bar. Don't worry about that too much, but that's in there. M is the mass of the electron. E is the electron's charge. R is how far you are away from the proton. So the proton is producing this electrical field, which is attracting the electron. And the field gets stronger and stronger when you get closer to the proton. And that's sort of showing up in this last term here, where you're taking psi and you're dividing it by r. So when you divide by something small, you get something big. So this last term becomes very important when r is small. In other words, when you're really near the proton. And then finally, well, let's see. Okay, so this Laplacian thingy I told you about before, that's just a thing that tells you how the wave function is curving. And this d psi dt is telling you how fast the wave function is changing. Before I wrote down something fancier that said d squared psi dt squared. That was about acceleration. This is just sort of about velocity. This is about the rate at which the wave function is changing. And then the piece de resistance, the scariest thing of all in this equation, is I is this weirdo number that people invented to be a square root of -1 back in the, when did they invent I? I don't know, the 1700s, I guess. So you may have been told at some point, right, if you square a negative number, you get a positive number. If you square a positive number, you also get a positive number. So there's no numbers that when you square them give you a negative number. So there's no square root of -1, for example. But mathematicians are not so easily dissuaded by their teachers. So sometime, some people realized, hey, it'd be really cool if there was a square root of -1, because I could solve so many more equations. And they said, well, let's try it, and let's see if we get in trouble. And it turns out they never got in trouble. So they said, okay, we can make this thing up. And it seems to work. Now, Descartes didn't like it very much, and he said that this number was imaginary, and that name stuck. That I stands for imaginary. But if you actually think about it very carefully, all numbers are imaginary. You don't see numbers out there in the world. Numbers are a creation of human thought that we use to help understand the world. So if making up some crazy new kind of number like pi or the square root of 2 or I really helps you understand the world, then you should go ahead and do it, as long as you can carefully make up the rules that you should obey when you're doing calculations with it. And so it turns out that that idea of imaginary numbers is fundamental to quantum mechanics. And in particular, while the wave that I was showing you for the drum was just a plain old ordinary kind of wave, where I just need a plain old-fashioned so-called real number to say how far or down this drum head is at any point. The kind of wave we need in quantum mechanics is more fancy. It's what we call a complex number that's something like 6 plus 5 times I. So it has a mixture of an ordinary real number and a real number times I, which we call an imaginary number. It turns out we need that kind of fancier wave to really describe what happens in reality. So I can't really say a whole heck of a lot right now about why we need this I, but I'll just say a couple of things. So the wave function that we saw in that equation on the previous slide, it's, like I said, it's not just a thing that gives you a number for each place in time. It really has two parts, a real part and an imaginary part, like 6 plus 5 times I. So 6 and 5 would be called the real part and the imaginary part. And that's because this wave that's happening in quantum mechanics, it doesn't really wiggle up and down as when you have a standing wave. It actually wiggles around and around in 2 dimensions. It's hard to draw. But the fundamental idea is that, like, if you have something going around and around in a circle, it's actually both going up and down, which is this red thing showing you how it's going up and down, but it's also going back and forth, which is being captured by this blue thing. So this is a little sneaky here, but this blue dot is going back and forth. And then because they didn't have enough room, instead of making this blue curve go up, which they should have done, I couldn't find one where they did that, they like bent it around so it goes across too. So if you ever learn this horrible subject called trigonometry, which is misleadingly described as the study of triangles. I mean, that's sort of what trig means, triangles. It's not really the study of triangles. It's true I could see a little triangle in here if I look really hard. There it is. But it's not really about triangles. That's a lie. It's really the study of circles. And it's just, and these functions called sine and cosine, you've heard of original sin. Have you ever heard of original cosine? So what they are really is just that to say where a point on the circle is, you got to use 2 numbers. One to say how far up and down it is, that's the sine, and one to say how far left and right it is, the cosine. The idea of complex numbers is to say, hey, we could combine those 2 real numbers as the real and imaginary part of a single complex number. So a complex number, it's nothing mysterious, it's just a point on the plane, like this green dot. That's a complex number. Its real part, the part that tells you how far across you are, that's this cosine. And its imaginary part is this sine. So it turns out that the waves in quantum mechanics, when they're standing waves, they're not just going up and down like this. They're really going around and around. But they're not going around in our 3-dimensional space. They're going around in some weird complex plane that's hard to imagine. So it's much easier to draw a wave that's just going up and down, and that's all I'm ever going to do here. So I'm just going to draw real parts of things, not the real and imaginary part. So in particular, this little picture here is actually a picture of the lowest shell in the periodic table. That is the lowest energy thing that an electron can do when it's going around a proton. It's actually a wave, and it's waving around. But it's really going around and around. But because I can't draw that, I'm just drawing the real part of it, which goes up and down. So you can see the proton would be right in the middle there. That's where the wave function is doing the most exciting things. And then it sort of fizzles out exponentially as you go further away. So that's the little lesson on quantum mechanics. Now let me just sort of tell you, like, okay, suppose you solve this Schrodinger's equation that I wrote down, and you try to find the standing wave solutions, the solutions that just sort of oscillate over and over again in some kind of sine or cosine kind of way. And it turns out that people can figure those out. That's like one of the major things you do in a course on quantum mechanics. It's actually a pretty darn hard problem to do. So you do various other warm-ups, but this is like the first problem you do that really has to do with the real world a lot, the hydrogen atom. And so the lowest energy state, well, this is a lousy picture. I may draw a better picture later. I sort of already gave you a better picture. This previous thing is sort of a better picture, but here, this is not three-dimensional. This is basically just showing 2 dimensions. You have to imagine there's a round thing that's waving around, and even more complicatedly, it has to be waving around instead of up and down. That's too hard to draw. You need 5 dimensions to draw that. So we'll just draw something nice and simple, a round blob, and that will be our basic description of what the simplest solution is. And that's the lowest shell. But it turns out that there are 2 ways to put an electron in that lowest shell, because there's another thing about electrons that I haven't told you so far that people learned a little bit later than this other stuff, which is that actually an electron is like a little spinning top or something like that. And it's also rather weird, but it can spin up or down. And the weird thing about it is that no matter how you turn our head, you always either see it spinning up or down. That may seem contradictory, right? If this is pointing up and I turn my head, it looks like it's pointing to the side. But electrons are weird. Anyway, it can spin up or down. And so there are 2 ways to get an electron into that lowest energy level. And so helium is just that. You've got 1 electron spinning up, 1 electron spinning down, and both in this spherically symmetric wave function, lowest energy kind of way. Then, if you look at the second shell, that is the higher energy solutions, that is solutions that wiggle faster, you find that there are 4 of them. There's 1 that's spherically symmetric, and then there are also 3 that look like these sort of dumbbell type shapes, and you can find them to point along whatever your favorite 3 axes are, here called the X, Y, and Z axes. And it's sort of an amazing fact that these 3 guys have the exact same energy as this guy. And I gave a more advanced math talk earlier in the day, which is all about why do these guys have the exact same energy as that? Because they look completely different, so why should they have the same energy? Well, they're secretly related in some way. But we got a total of 4 solutions for this second shell, but again, the electrons can be spinning up or spinning down, so we got twice that, 8 different ways to put an electron in the second shell. And you'll notice the cool thing is that the second shell sort of has like a mini version of the first shell in it. This blob here on top was what I drew you for the first shell. So it's sort of like Russian dolls with a little one inside a big one, and that continues. So like the third shell comes from 9 solutions of Schrodinger's equation. So there's a round one, there are 3 that look like dumbbells, and then there are 5 that are even more complicated that you see can have 4 lobes, 4 blobs. Those blobs are places where it's very likely to find the electron. And the white stuff means it's very unlikely to find the electron there. And it's a very simplified picture because it doesn't like suddenly stop like, oh, you can find it. No, you can't find it. No, it sort of fizzles out. So this should be drawn in a more blurred kind of way. But we're trying to keep it a kind of simple cartoon picture. So here we get 9 solutions, and double that, you get 18 ways to put an electron in the third shell. And as you see, the third shell sort of has like a mini version of the first shell and the second shell as part of it. So this picture is not completely crazy, although this is not supposed to be like a picture of anything you ever see in nature. It's just like a way to keep count of things. And so it goes on and on and on like that. Well, okay, I guess I went on a little bit more. So here's the fourth one, and now you have 1 plus 3 plus 5 plus 7, and if you work that out, hopefully that equals 16. So there's 16 solutions for this fourth shell, and that would give you 32 ways to put an electron in the fourth shell. Yeah, and it's got to be 16 because it's 1 plus 3 plus 5 plus 7, and it's 4 times 4 is 16. So that goes on, and so if the electrons weren't repelling each other, you'd have a noble gas like helium that filled up just the first shell, and then a noble gas like neon that filled the second shell, and that's really true, that's how it works, but then you'd like have another noble gas that filled the third shell and another noble gas that filled the fourth shell. And that's not the pattern that we actually observe in nature, and it's because the electrons actually repel each other, making the whole story a lot more complicated. But here's, anyway, is an animation of the first shell solution, which I sort of already showed you. So you have to mentally blend in your mind the knowledge that the first shell solution is some spherically symmetric thing with the knowledge that it's pulsing, which is easier to draw if we take a slice of that sphere. And this is a graph of how likely it is that you find the electron somewhere or other. And you see it depends on where you are, but also it oscillates with time. And these animations are way beyond my capability. These were made by John Bullock, who has a nice page of these animations. I was desperate preparing this talk, thinking I need good animations. I can't find them anywhere. There are some decent animations, but what I see in my head is much better than any of these things. I can see this spherically symmetric pulsing thing, but you can't see pictures of it on the internet. And so I think someday people need to sit down and make some really good pictures of what atoms are actually like. They're hard enough to understand even without, they're hard enough to understand already. Why also hit people with lousy pictures? But it's hard to draw really good pictures. So here's the second shell solutions. So you'll notice there's this spherically symmetric one that's drawn over here. But if you look carefully, this is a little bit different than the last one because this actually has more wiggles as we go out. It goes up and then it bends down a little bit and then it comes back up. Just like those drumheads, there's this first solution that just had like a mound, and then there's a second one that had a mound, then it went down and back up, and so on. And that's what's going on here. Then there are these solutions here that are not at all spherically symmetric, that are dumbbell shaped, and here's like a picture of how the wave function is oscillating for one of those. The others are just like rotated versions of that. And then the third shell solutions, again, you have a spherically symmetric one, some three dumbbell-shaped ones, and 5 of these more complicated ones. And you can see that these more complicated ones, you see it's like curving up in 2 places, and it's curving down in 2 other places. The probability that you find the electron is like the square of this function. So if this function is either positive or negative, it means you're likely to find an electron there, which is why in these pictures you see like 4 blobs where you're likely to see an electron. That corresponds to these 4 things. At any moment in time, 2 of them are poking up and the other 2 are poking down, but they are all places where you could be likely to find an electron in that state. And so this whole classification can be done. And it's sort of more elaborate than the classification for the drumhead that I started out with, but it's very similar in flavor. And it's part of a whole branch of math where people study standing wave solutions to all sorts of equations. There's a whole bunch of stuff to say about that. But I just wanted to pound in that this pattern here, that the first shell had one solution to Schrodinger's equation, one standing wave solution. And the second shell had 4, because that's 1 plus 3, but it happens to be 2 squared. The third shell has 9 because it has 1 and 3 and 5, but that happens to be 3 squared, and so on. And so part of the math that's going on behind this, which is some very old math that I'm sure ancient Greeks knew perfectly well, is that if you add up the first n odd numbers, you get n squared. So here I'm like adding up the first 3 odd numbers, and I get 3 squared. And so that's part of the numerology. That's not numerology in the bad sense, but the numerical patterns that we find lurking in the periodic table. So if you look at the periodic table, you'll see that this is hiding in there, but it gets a little more complicated than that. The first row of the periodic table has these 2 elements. That's when you're filling up the first shell. The next row of the periodic table has 8 elements. Count them, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. Well, but then the next row also has 8 elements, and so that's weird. You might have thought, okay, I should be getting 2 times the square numbers. Why did you say 8 twice in a row? What happened? Well, it's because the electrons repel each other, so the next batch of electrons that you start stacking on here are actually like not just filling out, they don't just fill out the next shell, they sort of, some of them hop up into a higher one of these subshells. So it's complicated, but the next row here has 18 elements, and then you see like the next one also has 18, so that 18 is coming in there, and it's because you've got electrons whose wave functions are following these different kind of patterns that I was drawing you the pictures of. So if you took a photograph of one of these elements, you would see that it was very likely to, I mean, how do you take a photograph of an element? Well, you do some experiment to check to see where the electrons are, shoot little things at it, and you could see that the electrons were likely to be in some places and not others, and that the kind of shape you would get would be these kinds of shapes, these different kind of blobby shapes. So atoms have that kind of shape. But it's really important to realize that what this shape is a shape of is it's the shape of where the wave function is big. So it's the shape of where you're likely to find electrons. If you actually look, where's the electron? You'll see, oh, it's right there. Or maybe it's there, or maybe it's there. It's always at some point or other. But this shape here is just the shape of where it's, of the probability cloud, the cloud of where you're likely to find it if you look. So that's this funny thing about being both a particle and a wave coming in. So there's a lot more to say about this. I hope it's clear that I've just sort of skimmed the surface of something. But there's also virtue in knowing when to quit, usually in the evening. And J.R.R. Tolkien has this nice song that repeats over and over in The Lord of the Rings. And you know, the little hobbit travelers start out very eagerly in the morning, and then by the end of every night they're like completely exhausted. And this is a version that's sung at night. Let someone else follow it who can. This road is going on too far. I at last with weary feet will take a rest. So I think you're ready now for a rest and maybe some refreshments, and so we'll stop here. Thanks.
So thank you very much, John, for that talk. We do have time for a few questions, but first I wanted to announce that there will be a t-shirt prize given out there. Some number of you will be lucky winners of a t-shirt, but I'm not going to tell you which ones are winners until after the questions. So force you to stick around a little bit longer. So we have time for 2 questions. Do you have one, or are you stretching?
No, I have a question.
Question.
So,
Yes.
you were talking about the shells, and you stopped at 4. Is there any reason not to go on to 5 and have 50? Or is 118 going to be a math?
Those higher shells, they do play a role in chemistry. But basically, as you get more and more electrons coming in, the repulsion of the electrons becomes sort of more important even than their interaction with the nucleus in the middle, or at least, let's say, not more important, but equally important. And so finding out, just seeing that 50 is like a real picking through a big mess to try to find some pattern that you know must be there. They're relevant, but they're like increasingly, you have to like work harder and harder to find them, to see them in the data.
I have a question. Sorry. I have a question that bothered me since I was an undergraduate in chemistry.
Okay, we're going to solve it right now.
Thank you so much.
Well, we'll see.
I've waited for 20 years.
Oh, the pressure's on. Okay.
Why is one of the orbitals different from the other 4?
Sorry, which one? What do you mean? Why is one? I don't know which.
It looks like a big 8 with a ring around it.
Oh.
There's still
Oh, okay. Yeah, so notice I cleverly avoided that picture. I didn't have that picture. I know what you're talking about. When you look at this third shell, sometimes people draw these, or maybe the fourth shell, sometimes people draw these in some funny ways where some of them look really different from the other. So the point is that one cool thing about this equation, Schrodinger's equation, is if I have two different solutions of it, like two different kind of waves, I can add them and get another solution. And so although I've drawn these as if like these are God's own favorite orbitals, I could have done other things. I could have taken this function, which doesn't look like a function, but is a picture of some kind of function, and added to this one, and then you get something that looked different. And so there's a certain amount of choice of how you draw them. And in some contexts, it like really makes a lot of difference which ones you use. And so that's why some of these funnier looking ones are often drawn in the literature. But there is a way to pick them so that they don't look like one of them is a weirdo. It's not like one of them is any weirder than the rest. If you think about it the right way, which is the way that I like, I guess by definition, that's the right way, right? So if you think about it the right way, there's not like one that's weird compared to the rest, yes. So that bugs me too, you'll be glad to know. Yeah. Yeah.
Your lanthanide and actinide series,
Uh-huh.
I see those normally going in and out or something along that line on these.
Yep.
They're filling the shell they filled out outer shells, now they're going back and filling inside shells. What's happening there the way?
Yeah, so you should ask the next speaker, who's hopefully a chemist. But so it gets very complicated. So I have a really crude understanding, but maybe that's better. Maybe that'll make it easier for me to make up something. So the idea is roughly that the electrons are repelling each other. So they don't see the lower energy shells that I've drawn here are actually close to the atom, and then the other shells get bigger and bigger and bigger. But if they repel each other, some of them would prefer to be far out. So what happens with these lanthanides, these rare earths, is some of them say like, hey, to heck with the rest of you. I'd like to start occupying a new shell. I'll have more energy because I'm further away from the proton, which I'd rather be attracted to, but I'll be away from the rest of you clowns who are like crowding around it, who are repelling me. And so they will fill out a certain part of a more outer shell. And then as you keep throwing in more electrons, that is, you keep on like going to higher rare earth elements, the next guys will go say, okay, I'll go and fill in the inside. But because the outer shell is sort of partially filled in the same way for a whole bunch of the rare earth elements, it means that the chemical properties of those rare earth elements, which are determined by what you see on the outside of the atom, are almost identical. So one of the things about the rare earths that like confuse the heck out of people is that they're like, I don't know how many, but sorry, I'm not a true chemist, but there are a lot of elements there that have almost identical chemical properties to all these guys. To chemically separate them is incredibly hard and difficult. And the reason why is because a whole bunch of electrons have decided to colonize some outer shell and then go fill in from then on in.
Does Schrodinger's equation have much to do with any of that?
Yeah, but it's a fancier version of Schrodinger's equation. So my version of Schrodinger's equation was really just about one electron being attracted to one proton. The real full-fledged Schrodinger's equation lets you talk about bunches of electrons all attracting and all repelling each other. And that's tons harder to solve. So this one that I wrote down, you could like solve with pencil and paper. But when you get like lots of things all interacting with each other, you basically ultimately need a computer simulation to solve it. Yeah. So people do that, and they do check to see that it's still working, but it's a lot more complicated. Mm-hmm. Yep.
Question here. Great presentation. I have a quick question. It's a little on the periphery, but I hope you can still tackle it. When you think about mathematical mysteries, and you look at, let's say, material science, there's a strong emphasis in that community of rigorous experimentation. Can you speak to the mathematical limits of relying on math itself? Do you see a few areas where there's an over-reliance on math? especially now with a lot of computational models. And so,
Well, people, I mean, if you allow me to go out of chemistry, I mean, so in economics, people completely over-rely on mathematics, right? So just because money is measured in a numerical quantity doesn't mean that like we have the foggiest clue of what people do, right? But because it's measured in numerical quantity, you can write down equations that say what you think people might do, and then you can base whole economic and political systems on it, and not surprisingly, they don't work quite as well as your theory predicts. So as you get towards simpler things, mathematics tends to work better, not because the math is better, but just because you're more likely to find a model that's simple enough that you can handle, that's still reasonably adequate to what you're trying to describe. So material science is a nice case of something that's pretty darn complicated. You can make matter with all these elements and do all sorts of crazy stuff with it, but it's still simple enough that you have a chance to do mathematical models of it. And there you see a really nice interplay between mathematics and experiment, where sometimes, for example, like high temperature superconductors, things that superconduct at temperatures like that of liquid nitrogen, which doesn't sound so high temperature, but that's a lot warmer than the previous ones. People have been seeking them for a long time, but the person who found them was someone who just like took different forms of clay with different minerals in it and baked them in ovens and tried and tried and tried until they succeeded. Then all the theorists who've been like theoretically trying to describe how you could cook up a high temperature superconductor, they had to race to catch up with that to try to then make a theory for how that worked. It could have worked out the other way, and sometimes it does. Sometimes people theoretically describe some new form of matter just by solving some equations, and then they tell people, okay, go out and make that. But both of those happen, and that's what makes that subject a lot of fun, because you get this interplay. So it's too complicated to figure it out by pure thought completely, but still pure thought can help a lot.
Okay, maybe 2 more questions. One over there.
Thank you. So this is a bit of a follow-up on his question, but as a chemist, especially a materials chemist, we look at the periodic table and we go off of our intuition. And there's really not, we don't think like a mathematician does. So is there any, like the mathematical visualization you showed us of the standing waves was pretty helpful in understanding these phenomena that we usually don't see as like understanding chemistry. So do you think there's any ways we think as a mathematician that can help chemists kind of think about the periodic table in new ways?
Think about the periodic table in new ways. So I mean, there's a lot that's mysterious about the details of the periodic table, and I think you need like a mixture of chemical intuition and solving lots of equations, which you need. They're complicated enough. You need to use a computer to solve them, to make progress on that. But just saying, oh, you need a computer to solve them, that doesn't mean like you say, okay, I'll just press a button on the computer and then it'll be solved, right? You need a lot of intuition as to like what are the right approximations to make. So there are a lot of nice approximations for wave functions of electrons in complicated, in big atoms or molecules, like the Hartree-Fock approximation, this and that and that. And mathematicians are busy trying to prove theorems about those approximations to say like how good those approximations are. And so I'm not into that field enough, so I don't know how much the mathematicians are actually helping the chemists. Of course, if you don't pay any attention to them, then of course they're not going to help you at all because you're not listening to them. But I'm sure they're trying, but then how much they're succeeding, I don't really know.
One more question. Do we have one more question?
The representations that you've drawn with the squares and the triangles,
Yeah.
is there a reason that you stack them in that particular way?
No. Well, basically no. Let's see. I mean, all I wanted to do, yeah, so don't take those things too literally. I was almost scared to draw these because sometimes like something is so cute that like it sticks in your head and you think, oh, that's what the whole talk was about. No, I just needed some way to draw a 1x1 square sitting inside a 2x2 square, sitting inside a 3x3 square, sitting inside a 4x4 square. So anyway, if you can, these are fun puzzles. So how many ways can you do that? I don't know. Stick a 1 by 1 and a 2 by. This is just one though, and there's nothing sacred about that particular one. Yeah.
Okay, well, let's thank John Baez one more time.
Thanks.
For a really
Great.
well-delivered talk, and now we have the lucky winners of,
Not yet.
Oh, yeah, sorry. Speaking of thanking John.
I'm a lucky winner. Oh.
John is definitely a winner. We have a nice thank you.
Thank you.
From the
Okay.
College of Sciences. And we thank you so much for
Thanks.
accepting our invitation.